Our last unit is relative motion, specifically relative velocities, and this Galilean transformation. So there's some fancy language going on here. But let's just take a look at a relatively simple example so that we can see the kind of idea that we're talking about. We're going to use an everyday type of example that I think is easily visualized to understand what we mean by these relative velocities and relative motion, and then we'll get to that fancy Galilean transformation language in a minute or two. So again, we have our inertial reference frame, so that's our blue reference frame, that's our XY axis, and we're going to have a primed coordinate system. So our unprimed axis is the at-rest, the inertial axis. This will be the ground or whatever. And we'll see, it doesn't necessarily have to be the ground. Whatever is at rest. So please get this into your notes. Now, the example that we're looking at here would be an example where, as I have here in purple, maybe you've seen the Goodyear blimp or just a balloon, a hot air balloon up in the air, but this balloon or blimp is going to have an engine. So if you think of the balloon starting down here on the ground, right, our inertial Earth reference frame down here on the ground, and it just goes straight up in the air. So just floats up with no wind, the balloon would just sit there. Now, as you can see, the primed coordinate system, the moving reference frame, is going to be the wind in the air here in this problem. In some problems, it'll be the water or current. And get this into your notes, because sometimes, believe it or not, it will even be the ground streaming backwards. So we'll see that in another page or two of notes. So our balloon that just went aloft, right? If there was no wind, it would just sit there. Now, if it was windy, and here I have the wind, decent wind, 20 mile per hour wind, blowing to the right, the person on the ground would see the balloon also going to the right at 20 miles per hour. Now, let's talk about our blimp now having engines. So let's go back to no wind and think about, okay, the blimp, the Goodyear blimp or whatever it is, goes up into the air. The pilot turns on the engine, and the engine is going to move the blimp at 10 miles per hour. Well, even without a wind, the person on the ground sees the balloon or blimp move 10 miles per hour. If we put both together, the wind at 20 plus the engine moving the blimp with respect to still air, as if there was no wind, you would see on the ground a total speed of 30 miles per hour. So all we have down here is kind of some math to go with it, and you can see at the very bottom we have this v equals v prime plus u. The primed coordinate system, right, is doing the moving, and the primed coordinate system velocity becomes the u vector, right? So that's the L. So the actual primed coordinate system motion is the motion of this variable L moving to the right. So the prime that we have in our v prime is what I have here, and I have it exploded because this can be a little tricky, right? The v prime is what's called the airspeed of the blimp or an airplane. If you hear the pilot say, we're moving at an airspeed, that's the speed of the plane without any wind. So that's what the engines are doing with respect to still air. So this is the velocity of the object in the moving medium. The moving medium is the u vector, and v is always the vector that, as seen by the at-rest observer, and in the example we just used, if we have both the wind and the engines, we would see 30 miles per hour. Okay, so please make sure you get down what you need there, and we can and will talk more about this in class, but that gives you the basic idea. All right, so the Galilean transformation is this equation, v equals v prime plus u. It allows us to transform, to go between. So it's a transformation. It goes between the moving reference frame, so the velocity of the object, v prime, in the moving reference frame, to a calculation for the velocity as seen in the non-moving reference frame. And u, of course, is the velocity of the moving reference frame. V equals v prime plus u. Now, this notion of a transformation equation, I added this into the notes because, believe it or not, you've seen transformation equations. Here we're going from the velocity vector in the moving reference frame world to the inertial reference frame world, but we already know how to transform from the Cartesian world to the polar world, right? The Cartesian world sees the polar world according to our cosine theta for x, and the Cartesian world y sees the polar world through r sine theta. This is a set of transformation equations that allows us to go between the polar and the Cartesian world. Now, some textbooks will use subscripts. If you look at the subscripts here, and I'll leave this to you if you choose to use it, I use v equals v prime plus u. It is the notation for special relativity. That's Einstein's relativity, so those variables will be familiar to you if you study special relativity. But if you look at the notation that's down here, it absolutely is the same as above, so it's your choice. So if you find you're struggling to solve the relative motion problems, and I'll give you a heads up, sometimes students do find these very kind of wordy and language problems, you can use kind of what's written here, the subscripts, the particle with respect to the Earth, the particle with respect to the moving frame, that's the v prime, and the moving medium with respect to the Earth. And you can see if you memorize how to handle the subscripts, you can set up the equation this way as well. So it is your choice. So get this into your notes, and we're going to do some examples on the next lesson.